Great, thanks. Thanks a lot, and thanks for the introduction. Hello to everybody. So I will talk about this part 1, evaluation of precipitation, but there is also part 2, which is about projections of precipitation at this kilometer scale resolution, and this will be presented by Emanuela in another session at EGU. I didn't list all co-authors here because the list is quite long, but I will acknowledge them at the end. So I'll start with the introduction, and this is basically that in the recent years we had these advances in computing power, and a number of studies started to appear that show improvements in model performance when the grid spacing is increased to a kilometer scale resolution and when parameterization of deep convection is switched off. However, these studies have been conducted over different regions and different models and different time periods. So there was no kind of concise message out of it. And this is where this Cordex FPS and EUCP Working Package 3 comes in. So one of the main aims of these two projects was to provide a collective assessment of our modeling capacity at the kilometer scale resolution. And this presentation here is basically kind of follows that, or it is the first step. It provides the evaluation of precipitation from these simulations through some simple indices. So on this slide, I show which model simulations we use in this work. So they are all conducted over this area shown in the picture here. So it is a greater Alpine region, and it is one of the mandatory domain for these simulations. And here is the list of all the groups that have been that have conducted these simulations. So the list is quite long, and we have managed to include all these simulations into analysis. So there are 22 simulations performed by 21 group. These simulations are conducted at the horizontal resolution of around 3 kilometers. And most of them also have intermediate step with the grid spacing of 12 kilometers or larger. And we also take these simulations into analysis to compare like what's the difference between the high resolution simulations and these coarser ones. As you will see here, there are two groups that do not use this intermediate step, and this is UK Met Office and the University of Gießen. In this group of the simulations, we have 6 different regional climate models, and we conduct these simulations for a 10-year long period, so from 2000 to 2009, and all these simulations are driven by ERA interim reanalysis. Here is just shortly a list of observations that we use for evaluation of precipitation. So the first one is Euro4M APGD data. It's a daily precipitation data with a horizontal resolution of 5 kilometers, and it covers this Alpine region. Then we have gridded hourly precipitation data set over Switzerland. This one is available with the horizontal resolution of 1 kilometer. Then over France, we have COMI4 data. This one is also with a resolution of 1 kilometer. And the last one is GRIPHO. It's a hourly gridded precipitation data set available over Italy at a horizontal resolution of 3 kilometers. And here is just a table of the indices that we look into. So they're very simple one, like mean precipitation, precipitation frequency, precipitation intensity, and then for heavy precipitation, we use percentiles. And we look into that for both daily and hourly precipitation. It is important to know that we calculate percentiles using all events, so including wet and dry events, and not only wet events as it is done in some previous studies. Before we do any kind of analysis, we remap, interpolate all data, all this high resolution data to a common 3-kilometer grid. And the intermediate simulations, we interpolate them to a common 12-kilometer grid. So after that interpolation is done, we do the calculation of the indices and then comparison with the observations. So here is the first results which we will see, and this is the multimodal mean of daily precipitation in the summer season. So this is the mean precipitation, and here we see these spatial patterns of the precipitation, and we see that both models actually capture these spatial patterns, although we see also some underestimation of these peak precipitation, especially over these mountain ranges. Then we also look into the intensity and frequency, and here we also start to see bigger differences between the 3-kilometer models and 12-kilometer models. So the 12-kilometer model tends to overestimate the frequency of precipitation and underestimate the intensity. So when you look into the mean, at the end it looks okay, but this is for the wrong reasons. On the other side, the 3-kilometer models, they tend to kind of reduce these biases. So the intensity and the frequency is better reproduced, although there are still some underestimation. And then we have heavy precipitation. So this is heavy daily precipitation defined as a 99 percentile, and here the difference between the two models is even larger. So again, the 12-kilometer models largely underestimate the intensity of the precipitation, and the 3-kilometer model perform much better. So the same analysis has been done for hourly precipitation, and here the conclusion is basically the same, but the differences between the models here are even larger. So as you see, the 12-kilometer model doesn't at all produce this high intensity precipitation as we find in the observations, but overestimates the frequency. And the 3-kilometer model on the other side performs much better. So these two slides were shown as a multimodal mean, but we can also see what's the difference between different models that we have in this ensemble of simulations. And so this is what you can see in this slide. So you have different models at the 3-kilometer resolution on the left-hand side, and then different models with a horizontal resolution of 12 kilometers on the right-hand side. And what you can see is that there are quite large variability between the models already within for the same resolution. But there is a clear difference between the 3-kilometer models and the 12-kilometer models, and this is that almost all 12-kilometer models tend to underestimate the intensity of this heavy hourly precipitation. The next thing that we look into is relative bias, and we again start with the daily precipitation. And here just a bit of explanation of this plot. So here you see like these boxes split into two triangles, and the uppermost triangle shows the relative bias for the 3-kilometer simulations, and then the bottom one shows the bias for the 12-kilometer simulation. And here we have for daily precipitation over the entire alpine region, so where we have the observations, and we have it for different seasons. And we see this clear difference between this colder kind of season, this winter and spring, and then also between this summer season. So in summer we have this large or underestimation of precipitation in almost all simulations, while in winter season we have overestimation of precipitation. And what you can also see is that this underestimation of precipitation is mostly quite pronounced for this WRF group of the models. But if you look into more details into this plot, you will see that in many of these boxes, the upper triangle shows kind of this reduction in the biases. So it means that the 3-kilometer model performs better than the 12-kilometer model. And then the same we have for the hourly precipitation, and here we split it according to the regions or countries where we have the observations. So the first one is Switzerland, and here I think is probably the most clear picture that we can see, and this is this overestimation of frequency and underestimation of precipitation intensity, which is quite pronounced, like in almost all regions except for summer. But in these many of these boxes, again, you can see that the upper triangle shows kind of this reduction of the biases. So this is the area of Switzerland. And then we also have the region of France and Italy. So it kind of holds a similar story, but the picture is a bit more kind of messy. And in some of the cases, you can also see like this switch from underestimation of precipitation intensity in the 12-kilometer model to overestimation in the 3-kilometer model, or this slight overestimation of that precipitation. And I think we are quite happy with that, because the observations also have their own shortcomings and tend to underestimate the precipitation intensity. And the last thing that I want to show you is a diurnal cycle of summer precipitation. So this is something that we already knew from before, but now we can also assess it from this multi-model ensemble approach. And the first kind of part of this picture is just this multimodal mean of these simulations, where we see these clear improvements in the simulation of a diurnal cycle of mean precipitation, wet hour frequency, and heavy precipitation. So these 3-kilometer models reduce kind of these biases in the diurnal cycle of the precipitation. And again, we can look into the spread between the models, and it kind of tends to be a bit messy, but I think what we can see is for this wet hour frequency and heavy precipitation is that these models tend to group together. So this 12-kilometer model, these thin blue lines tend to kind of group around this thicker blue line, and the same for this higher resolution model. So it's not that they're kind of produce something completely different. So this is the area of Switzerland.
Sorry, Nikolina, I think we have to close because we're at 14 minutes already.
Okay, so I just finished now. Yeah, so this is just then very similar for France and Italy, and I come to the summary where I just conclude that we think that this approach is kind of a promising way for improving climate simulations, but there are a few notes to kind of keep in mind, and these models are run for the first time at such a high resolution, and no prior calibration or tuning has been performed. They depend on driving data, so their performance is only good as the input. and they need high resolution observations for evaluation. And they're still using the parameterizations which are designed for coarse resolution models, and maybe they don't hold that good at the kilometer scale. And then just the last slide with acknowledgements to all co-authors, and many thanks to all of you for listening or reading and commenting later. And I'm sorry for the going over time. Thanks a lot.